Okay, so let's look at signals in communications. So this is part of our analysis of data, audio, video, and images. Okay, so we're all accustomed to frequencies that we hear within music. So we have a C, which is at 32.7 hertz. And then what we have is we have octaves. So octaves are a multiple of the base frequency. So we have our second octave here, third, fourth, and so on. And these are multiples of the original frequency. In waves, what we have is that we have what's called a frequency domain and a time domain. In the time domain, we see signals such as this. This is a sine wave, and the sine wave has a certain period called t in this case. It goes from to a certain height, in this case V max, down to V min. But we can also analyze this with inside the frequency domain. And the frequency is actually 1 over t, which is the repetitive period. And if we plot a pure sine wave on a frequency plot, we see a single line at that frequency with a certain amplitude of the waveform. So this is our representation here of our sine wave. That's the amplitude. Sine 2 pi f is the frequency, and then t is the time, and then theta is the angle, the delay, the phase delay. So let's have a look at some real plots. So we'll just go to the site here, and we'll have a look at what our plots look like. Okay, so here are a number of repetitive waveforms. So we have a sawtooth waveform. We can set up a certain frequency. So if we reduce the frequency, then we should be able to see that we get fewer of these waveforms within the same time. Our triangular waveform goes up and down within the same in repetition. Sine wave, as we've seen, has this format. Square wave, Gaussian pulse, and a chirp. So one thing to notice is that when we use our repetitive waveforms, what we see is spikes. So this spike here is at 2 hertz. This is at 4, 10, and so on. So the actual frequencies within our waveforms, if it's a repetitive, are actually discrete frequencies. So we'll just increase that to 5 again. Okay, so there we are at 5, there's 15, 25, 35, and so on. If it's a pure sine wave of 5 hertz, we see here we have a peak at 5 hertz. The square wave we'll see later in the module, but it has certain frequencies here. See one at 5, 15, 25, and so on. This is a fairly distinctive feature of a square wave in that we get what's called odd harmonics. So this is the first one here, and then we have one at 3 times that, and so on. Okay, so odd harmonics are at 3, 5, 7, and even harmonics are 2, 4, 6, and so on. Another concept that we have with inside communication systems is the concept of a bandwidth. And the bandwidth is really equal to the measure of the range of frequencies which can actually go through the system. It typically has a lower frequency that passes in a higher, and the bandwidth is the difference between the upper and the lower frequency. So typical bandwidths that we see are with speech 4 kilohertz, 4000 hertz. With hi-fi we have around 20 kilohertz. FM radio we have a bandwidth of about 200 kilohertz. TV 6 megahertz, and for satellite communications it's about 500 megahertz. So this defines it's related to the amount of data and information that we can actually send. The higher the bandwidth, the more data that we can actually send through the channel. Okay, so this shows our frequency spectrum. In this case, we have fairly low changing spectrum here, and we can see here that we get a response where there is more significance for the lower frequencies. But whenever we have higher frequency changes, such as this one here, we actually see higher frequency components coming in. Okay, so the faster the change of a signal, the higher the frequencies that we'll actually have within it, or the more significant that they'll actually be. So a slow moving signal will have low frequencies, where a higher changing signal will have higher frequencies contained in it. So this shows the waveforms that we have. So in this case we have a fundamental frequency of F1. It has a certain amplitude, and then we have a second harmonic, third harmonic, and so on. We can see here for this one, the waveform has these harmonics added to it. In this case, this is the strength of the first harmonic. This is the second, third, fourth, and fifth, and so on. And these frequencies together, when they're in phase, gives us this waveform. So let's have a look at that in real life. Okay, so we can say that we have 0.6 of a second harmonic and 0.2 of a third, and we'll have a look to see what that looks like. Okay, so we can see here the distortion that the extra harmonics actually have. If we take away all the amplitudes there, what we should see is that we get our sine wave back and we get our amplitude here. But if we add in second harmonic, we can see here it starts to distort, and then we'll add in a third harmonic, and you can see it's adding these higher frequency changes within it. Okay. And when it comes to overall bandwidth, what we have is that we're limited to the lowest bandwidth of the whole system. So in this case, even though we have 100 megabits per second and 200 here, the two limiting factors are the 64 megabits per second parts, so that the overall bandwidth that we get is only 64 kilobits per second. So let's look at signals and distortion. So our signals might start off perfect, but then we get noise added to them. So three common sources of noise are thermal noise, and that's to do with the noise that's generated inside electronic devices. And that thermal noise is equal to K, which is the Boltzmann's constant, times the temperature, which is in Kelvin, and then times the bandwidth of the channel. So as we increase the bandwidth of the channel, we will increase the thermal noise that's generated within it. We also get crosstalk when we have two signals that are near each other and they're not shielded enough, then the signals in one can actually affect the signals in another. Equipment which is close by can also affect the signals within inside our systems. And then we also get impulse noise, and that's typically caused by things like a motor starting up, and it causes a little spike on the system. So here we see a sawtooth wave with some noise in it. So the sawtooth wave is meant to be like this, but we've added in what's called Gaussian or normal distribution noise, and that becomes a random factor in changing the signal. And we see here in our waveform that it's added other frequencies apart from our nice harmonics that we had before. So let's have a look at this one. Okay, so here is our signal without our noise, and what we'll do is we'll add in a 0.2 amplitude for our normal distribution noise, and we can see straight away it affects the noise. So it's a random generation that we have here, so the peaks and the spikes will not always be the same. And we see here what's happened to the noise and to the frequency response. It has changed and added extra frequencies into the waveform. One way that we can filter this is that we can actually define what's called a noise threshold, and we can then filter out anything which changes too fast. Let's have a look at our sine. So our sine, we've lost our lovely looking sine when we add noise to it. If we try 0.1, so we actually see that it just distorts that a little bit, and we can see the noise sitting along here. The limit that we have really upon the capacity of any link that we have is related to the signal power and also the noise power within inside the system. So we define what's called the signal to noise ratio, and the signal to noise ratio in decibels is really just the power of the signal divided by the noise power, and then we take the log of 10 and multiply it by 10, and that gives us our signal to noise ratio in decibels. If we take an example of 100 milliwatts and 20 nanowatts for our noise power, and then we get this value here, which gives us a signal to noise ratio of 6.7 decibels. Once we have the signal to noise ratio, we can actually work out what the capacity of the link actually is. If we take our signal to noise ratio, add 1 onto it, and then take the bandwidth, that's log to the base 2 of this value, then we can work out what the capacity of the link actually is. If we want to calculate log to the base 2, it's quite easy. We take the log to the base 10 of the value, and then divide it by log to the base 10 of 2. So it's quite easy to convert in them. So let's take an example of 10,000. So with 10,000, we end up with 1 plus 10,000, and we take the log to the base 2 of that. So that becomes the log to the base 10 roughly of 10 to the power of 4, divided by the log to the base 10 of 2. And then we do the calculation there, and we see that it's 13.3 times 10 to the 5 bits per second. Okay, so the main thing here is that the capacity of the link really is related to the signal to noise ratio. If we can make this high, then it increases our capacity. Okay, so that's been a brief introduction to signals.